Swayam Prabha. Digital India. Educated India.
Today we will extend the transverse vibration by using the transfer matrix method. Now we will consider a intermediate support when in a continuous rotor. If there are intermediate support, which is very common in practical rotors, then how transfer matrix method can how we can able to handle such situation. Also, gyroscopic effect in rotor system when we are dealing with the transverse vibration is very common, especially when we are dealing with the high speed rotor cases. So, that also will cover in the present lecture, okay, how this particular gyroscopic effect influence especially the point matrix in the transfer matrix method. Also will through some examples we will try to see how these methods we can able to apply in some simple cases, but with the main idea of that those examples will be to illustrate the method for simple case, but once we understood the method completely, then the extension of that for a large number of rotors or large number of discs is straightforward. So, let us see what are the things we will be covering. So, again we are dealing with the transverse vibration, TMM method, free and forced vibration we will be covering, and basic concepts would be similar to the previous one. Some of the things like boundary condition, frequency equation. Now, this frequency equation, especially when we will be considering gyroscopic effect, we will see that the natural frequency will depend upon the speed of the rotor itself. So, as such, the form of the equation, whatever the frequency equations will be there, that will be having more complexity. Also, how to tackle the intermediate support in the rotor system, we will take one example for this particular case, and will illustrate that there is some difficulty if we have intermediate support using the transfer matrix method, and how the gyroscopic effect changes some of the terms in the point matrix we will see, and through some example we will try to see these cases. So, let us take one example in which we have one intermediate support in a rotor system. So, example is like this. We have a shaft which is massless, we have a disc at the overhang part of the shaft, and these are the pin support or simply support, and this is the intermediate support. Basically, we need to obtain the natural frequency or the critical speed of the rotor system. We have mass and diametral mass moment of inertia property of the disc. Various dimensions are given, like A is the length of this overhang part of the shaft, and B is the this part of the shaft, and diameter is uniform, is having 0.01 meter. In this particular case, we are not considering the gyroscopic effect. Generally, in overhang portion, we expect a lot of gyroscopic effect, especially when rotor is having high speed, but for this particular case we have neglected that. So, main focus of this particular example is how we can to handle the boundary condition at the this particular intermediate support case. This support and this support will see that there is some difference in the conditions which create some problem in transferring the state vector of the rotor from this side up to the other side. So, because this intermediate support gives some kind of unknown reaction, and that unknown reaction create a difficulty in transferring the data state vector from left of the support to the right of the support. So, we will see how this can be handled in the present example. So, this is the diagram of the O-ring rotor. You can see this is the station 0 we have selected, station 1 is at intermediate support and station 2 at the other support. Now, I have taken the free body diagram of the shaft segment. So, just left of the support up to this is the free body diagram for that particular shaft segment. So, you can able to see this is the disc, this is the shaft which is just before the left side of the support. In this free body diagram, I am attaching the shear force and bending moment at this end. Also, at this end, shear force and bending moment corresponding to node 1, which is basically left of the support 1. So, we are attaching L to represent that this is from the left of the support. Now, this is the shaft segment which is just right side of the support up to this point. So, this is the shaft segment free body diagram for the second shaft. Here this is the shear force bending moment, and shear force and bending moment we are applying. Here, to distinguish the shear force and bending moment toward the right side and the left side, we have represented this as right of the support, these two, and in this basically this is simply supported end condition. So, these are the shear force and bending moment corresponding to this end. Now, you can able to see that this here and here, because these are toward the left and right of the support. So, now we have taken the free body diagram of the shaft segment which is at the support. So, this is the shaft small segment, this is the support, this side we cut the shaft and we drew the free body diagram of the shaft segment 1. Similarly, we cut the shaft here and we have drawn this. So, obviously, whatever the shear force and bending moment is acting here will be acting here, but its direction will be opposite. So, this is the left of one support, shear force is also left of one support, but direction is here it is downward, this is upward. Similarly, this moment is counterclockwise direction, this moment will be clockwise direction. Similarly, in this end of the shaft segment, this shear force and bending moment will be same, only thing their directions will be opposite. And because we removed the support also from this, so we expect a reaction force from the support. So, I am representing that reaction force onto the shaft as Ra. So, this shaft segment is acted by the shear force and bending moment toward the left side and also toward the right side, and here there is a reaction, unknown reaction from the support. So, now you can able to see that this reaction force which is unknown will create problem in transferring the state vector this side to this side, because one unknown reaction is there. So, now let us see how we can able to solve this problem. So, in this particular case, first I have taken the segment 1 and I have written the state vector which is left of support 1 and the state vector at 0 station. So, you can able to see this is the state vector at 0 station. So, we have point matrix first for the disk and then the field matrix. So, point matrix into field matrix. So, this is the transfer matrix for transferring the state vector from 0 station to left of disk 1 or support 1. Similarly, this is the shaft segment 2. In this, the support is this end. So, you can able to see that now we are writing the state vector relating with the right of 2 right of one state vector, that is right of one support, to the left of 2. Left of 2 is here, and in between we have only shaft segment, there is no mass, there is no disk. So, only field matrix will be multiplied here to relate the state vector right of support 1 to left of 2 station. So, in between these two we have the support. Now, let us see the free body diagram of the support. So, free body diagram of the support is this one, which we drawn earlier. Now, you can able to see that the boundary condition, apart from the support, what are the boundary conditions we have in the overall system. So, at station 0, which is a free end, we expect that the shear force and bending moment will be 0, because we have a rotor system like this. Here one intermediate support is there, here one support is there, this is 0 station 1 2. So, at 0 station we have free end condition. So, shear force and bending moment will be 0. At station 1, which is at support, the displacement at station 1 y1 will be 0, and in this particular case the bending moment which are there in the right of support 1 and left of support 1, they will be equal, because from they will be equal, and you can able to see that they will not be 0. As also from free body diagram of this, if we take the moment balance or force balance, we will see that there are 3 forces. One is left of support 1 shear force, which is, let us say, positive y direction, right of support 1, which is downward direction, so negative, and the reaction force at RA at station A or the support A. So, that is the, so this is the force balance at support at station 1. Now, at station 2, what is the boundary condition, which is simply support. Station 2, we have displacement y2 is equal to 0. Also, the bending moment is 0, because simply supported end condition, which is for station 2, here we have simply supported case, but intermediate support is different as compared to this simply supported case. Here displacement is 0 as well as moment is 0, but here displacement is 0, but moments are not 0, as we have seen in the previous expression. So, moments will not be 0. Now, so we have all the we have looked into all the boundary conditions at station 0, 1 and 2. Now, let us see this is the equation corresponding to the first equation which we wrote. This equation, this is relating the state vector as 0 and left of station the support 1. So, 0 and left of support 1. In this particular case, at support 1 we have seen that the displacement is 0, y1 was 0. So, we have kept this as 0, and at station 0, because this is free end, bending moment and shear force both are 0. And if we expand, let us say the first equation of this, so we will get 0 is equal to minus of u11 into y0, because that is belonging to the station 0, u12 into phi x naught, because this is belonging to the station 0, is equal to 0, because these two terms will get multiplied by this and they will not contribute to the first equation. So, we have taken first equation because in the left side it is having 0 quantity, which is known quantity. In other equations we have unknown quantity. So, that is why we have taken the first equation, and with this equation we can able to relate the angular displacement at 0 station and the linear displacement at 0 station using this relation. So, you can able to see now we related these two angular displacements at the station 0. Now, we are again coming back to the conditions at the support. At support, what are the conditions we have? We have y1 is equal to 0, that is the displacement at station 1 is 0. Moments are not 0 at left and right side, and shear force are the force balance is containing the shear force, also the unknown reaction force. Now, I want to put all these equations in a matrix form. So, apart from this, you can able to see that the slope of this particular shaft will be same in both ends. That means, we will be having additional condition that phi left of 1 is equal to phi right of 1. Similarly, so you can able to see the first this matrix which I have combined all these equation, what they represent. So, first equation is minus y, which is right of 1 is equal to minus y left of 1. Basically, both are 0. So, they will be representing 0 equal to 0 terms. Similarly, the second equation is this one, in which the left and the right side of the slopes are same. So, if you expand the second row, second equation, you will get this equation. Third equation is the moment equation. This is the moment equation, both are same. So, these two moments you can able to see, if you expand the third equation, you will get moment in the right of 1 will be equal to moment in the left of 1 side, because this 1 is there. When we are coming to the shear force equation, this one. So, we have right of 1 is equal to left of 1 and the reaction of this particular support, that is also there. So, now you can able to see that we have both are positive. So, right of 1 is equal to this plus this. So, if you expand the fourth equation, you will get the exactly same equation as this one. So, you can able to see that we have included the reaction force inside this particular matrix, and this particular matrix I am representing as U star for support, SP is for support. So, this particular transfer matrix is transferring the state vector which is in the left of support at station 1 to the right of support at station 1. So, as earlier we had point matrix which was relating the state vector at either end of the disk. Similarly, this particular matrix will relate the state vector at either end of the support. So, left to the right. Now, coming to the transfer matrices which we developed earlier. So, first we developed for segment 1. So, this is the relation for that, in which station 0 and 1 we related. In previous, using support conditions, we developed the state vector between left of 1 to the right of 1 of the support, and from segment 2 shaft, earlier we related right of 1 state vector to the left of 2 state vector. Now, we can able to see, we can able to combine them. How we can able to combine them? We can able to substitute this here. Also, we can able to substitute this here. So, if you substitute, you will see that we are relating the state vector of left of 2 to the 0 station, and in this not only the transfer matrix for shaft segment 1 and 2 is there, but also for the support is also there. So, if you multiply these matrices, we will get a transfer matrix, overall transfer matrix. Now, the form of the overall transfer matrix is very important here. So, if we multiply these matrices for illustration, so if we multiply it, we will see that the support reaction Ra, which is unknown, will be coming in the last column like this. Other quantity will be a known quantity. Only the unknown terms I have highlighted here because that is main important thing. In this, all these will be containing the mass, stiffness terms of the shaft, the disc and the shaft, also the natural frequency, which is also unknown, but the reaction which is unknown will be in this particular column. Now, we can able to apply, because now this is the overall transfer matrix. Now, we can able to apply the overall boundary conditions of the problem. So, at node 2, we have this particular displacement equal to 0, because this is a simply supported condition. At 0 station, this station we have free end condition, so bending moment and shear force are 0. So, you can able to see this particular equation will take this form, in which these two are 0 and this is also 0. Now, once we have this, now you can able to see in the left side. Now, we have, apart from this, there is a at station 2, which is simply supported, the moment is also 0. So, you can able to see this moment is also 0. So, in the left hand side we have two terms which are 0. So, we will be taking out the first row and second row equations from this, and if we write that, we will, you can able to see, if I write 0, the first equation of this will be T11 minus y, this will get multiplied with that, then T12 phi at 0 station, these are for 0 station, 0 y 0 minus I am taking out, and other two terms are 0 0 multiplied by, that is T15 into Ra, and that is multiplied by 1. So, this is Ra. So, now you can able to see this is the first equation. Similarly, the third equation will give us another equation, T21 minus y naught and plus T, this is 31 and 32 phi naught and then T35 Ra. So, this is the third equation. So, these two equations we can able to put in a matrix form now. How we can able to put? We can able to put in the matrix form like this. This is the that particular equation. So, this is the equation of the first and third. Basically, this is the equation for the second and fourth equation of the previous equation, but we are at present we are interested in this, in which we have these two equations are basically these two equations from first and third, which we expanded. The second and fourth will give this equation. So, now we are focusing on this equation, in which we have 0 terms in the left hand side. Earlier, if you remember, we had the state vector at 0 station related by this expression. This we related earlier. Let us see back that relation. So, this is the relation which we developed earlier. So, this equation will be using here. So, I am using phi naught. So, this is the phi naught. So, in this equation I am substituting this one. So, you can able to see that once I will put the phi naught here and I am multiplying with this matrix, I will get this, because now this phi naught will come here and then y naught will be common, and whatever the remaining terms I have multiplied. So, that multiplication will give me this, and y naught is common, and this term. Now, these two equations now containing only two unknown, one is y naught and another is R A. These two equations we have obtained by using this. So, basically we have eliminated the phi naught from this, and this equation we can able to write it like this. So, you can able to see we have rearranged basically these are two equation and containing two unknowns, but these are homogeneous equation. So, I have substituted rearranged this in this form, in which two unknowns I am writing now in this form. So, now you can able to see this homogeneous equation, non-trivial solution of this. That means when we do not want the R A and y naught to 0, we need to have determinant of this to be 0. So, that will give us the frequency equation. So, this is the frequency equation, determinant of this, and for various values of the parameter, if we substitute in this, because t's and u's they will be containing only unknown as omega. So, we will get a polynomial. In this particular case only single disk is there, and we are considering 2 degree of freedom of that disk, there is a linear and angular displacement. So, we expect 2 natural frequency. For that obviously this frequency equation will be quadratic in nature, and we can able to get the 2 natural frequency from this. And this same problem we solved using transfer matrix method earlier using influence coefficient method, and the values are very close to those values. So, through one example we have seen that how we can able to develop the transfer matrix for the support, because support contains one unknown reaction. So, we based on the free body diagram and the boundary condition at the support condition, we develop the transfer matrix, and then from that we have obtained the frequency equation. This particular method we can able to apply for multiple supports also, and now we will take up another complexity in the rotor system, that is a gyroscopic couple. As you know, gyroscopic couple generally occurs onto the disk having large polar moment of inertia, and we expect that the change in the transfer matrices will be on the point matrix only, because shafts, when we are considering massless as we have modeled till now, they will not be having any gyroscopic couple, only the disks will be having gyroscopic couple. So, now let us see how the gyroscopic couple will affect the analysis. So, in the previous lectures when we have dealt with the gyroscopic effect, we obtained the gyroscopic effect expressions. Now, we will be using them directly here. Only thing is, in the disk case, when there is no gyroscopic couple, earlier when we are developing the point matrix earlier in the previous lectures, we had these kind of moment equation, only this term was not there. So, we had moment balance of the disk from free body diagram of the disk, and these are the bending moment, and these were the external bending moment acting was equal to the inertia, rotor inertia of the disk. Now, because of gyroscopic couple, apart from this there will be additional term of the gyroscopic couple which will be coming. In this you can able to see that this particular angular displacement will be of the other plane. So, when we are considering the YZ plane, the angular displacement in that plane of the disk is phi x, but the gyroscopic couple will be because of the angular velocity or the angular precision in the other plane, that is zx plane. So, that is why this angular velocity or angular precision is phi y instead of phi x. Now, this is one of the equation which will be affected. Apart from this, the bending moment in zx plane also we need to write here, and in this particular case one additional gyroscopic term, this will appear apart from the rotary inertia. In the development of the point matrix, we consider only single plane, but now because of gyroscopic couple, what is happening, both plane are involved. So, we need to write these equations for both plane. So, that is why we have written for yz plane and for zx plane. Now, you can able to see the state vector. If you want to see the state vector in this particular case, in the previous lecture I have explained how we should stack the state vector if we are considering damping or the gyroscopic couple, and I mentioned that the state vector will be having 17 into 1 size. So, let us see how the state vector will be representing in this particular case. So, this is the expanded form of the state vector. So, basically transpose of this will give a column vector. So, in this particular case we can able to see that the x displacement, but real part of that I am stacking first, and the angular displacement about y axis, bending moment in the zx plane, shear force in y direction, in x direction. So, and all these are corresponding to the real part of the state vector. These next 4 from 5th to 8 is the imaginary part of the same state vector in x vy and zx and sx direction. So, first 8 vector are belonging to one plane, that is zx plane. First 4 is real and next is the imaginary part of that. Similarly, in the 9 to 16, this another 8 state vector will be representing corresponding to zx plane or zy plane, and first 4 is for real part and next 4 is for the imaginary part. That means, each displacement which is there will be representing as imaginary and real. Similarly, y and other displacements and also shear force, bending moment, every one will be having 2 parts, because now we are considering 2 plane. So, their phase may be different. So, to take care of that, we are writing them in a form of a vector or a complex quantity. So, you can able to see this is the stacking of the state vector. Now, coming back to the previous equations, you can able to see that in this state vector, the 3rd, 7th, 11th and 15th terms belonging to the moment equation. That means, again go back to the previous one, 3rd, 7th, 11th and 15th, these are belonging to the moment equation. So, that means the changes will be there in these particular rows in the point matrix, because gyroscopic couple terms are giving additional terms in these rows, 3rd, 7th, 11th and 15th rows. Now, when we are talking about the angular displacement, because this gyroscopic couple is containing the angular displacement. So, again when we look into that state vector, we will see that the 2nd, 6th, 10th and 14th are belonging to angular displacements, 2nd, 6th, 10th and 14th. So, these terms will be coming on the 2nd, 6th, 10th and 14th columns. So, they are in the rows. So, basically in the point matrix they will be coming in the 2nd, 6th, 10th and 14th rows. So, the position of these terms will be 3rd row, 7th row, 11th row and 15th row in the point matrix. Their column will be corresponding to the angular displacement, that will be 2nd, 6th, 10th and 14th. So, now let us see one of the equation. We will expand and see how they will change the point matrix. So, I am writing the angular displacement in their real and imaginary part, and similarly moment also I am writing the real and imaginary part. So, basically this is a this quantity will give the amplitude and phase information, and this is the frequency component of the moment. Similarly, this will give the phase and amplitude part of the angular displacement, and this is the frequency. So, if we substitute this in the first moment equation, this moment equation, so this is belonging to the right of m y z. So, the first moment equation, moment will give this minus the second moment and is equal to this is the rotary inertia. So, because here second derivative is there, so we need to take second derivative of this. So, we will get this new omega square, second derivative will get derivated because they are not time dependent, and the bending this gyroscopic couple will give one term because this is only derivative with respect to one time t. So, that means when we differentiate this once we will get j nu. So, that is why this complex term is coming here. So, this is belonging to the gyroscopic couple in that yz plane. Now, if we take the real part of this and imaginary part of this, if we equate, we will get this as a real part. So, you can able to see first term, this term, then real part of this, and because this j is here, so this will be real now. So, that is why this is coming here. So, this term will come here. Similarly, this is the imaginary part of this equation. So, now let us focus on this equation. So, this equation is basically we have the real part of the bending moment in yz plane. So, let us see what is the where it will be there. So, this is basically rho. So, yz real. So, if we see in the state vector, this is yz and real, and this is the yz imaginary, but that expression is yz real. So, this is the 11th row. So, we have 11th row in the point matrix, and this is the additional term basically in the gyroscopic couple. So, this is phi y imaginary, j is imaginary. So, let us see what is the position of that. Phi y imaginary is here 6th. So, we will be having 6th column and 11th row. This particular term will come in the point matrix, because point matrix is, as I mentioned, will be 17 into 17, and this particular term will come in 11th row and 6th column. Similarly, if we say this equation, this is the yz in the imaginary. We have seen that this was coming in the 15th row, and this angle phi y real, phi y real is here, that is the second position. So, that will be in the second column. So, this term which is coming from gyroscopic couple will be affecting the 15th row and second column in the point matrix. So, this is the I have rewritten again here. So, 11th column 11th row and 6th column, this term will be coming, and 15th row and second column will be this. So, these two are coming from these two equations, which in turn is coming from the first equation. So, because of this we got two terms in the point matrix, additional term. So, similarly, if we take this equation, if we expand it, we will get additional 2 terms, and there we can able to check that at the 3rd row and 14th column and 7th row and 10th column, this term will be coming. So, in total we will be having 4 entries which will be new because of gyroscopic couple, because these are only coming because of gyroscopic couple. Other terms will remain same as the previous one, only these 4 entries will be new in the our point matrix. So, let us see what will be this transfer matrix over one disk. So, this is the overall transfer matrix, this is the point matrix, modified point matrix for a disk, ith disk. Earlier we had this form of the P, in which we had this as 17 into 17 size, and we had P matrix at the diagonal place earlier. This is the P matrix which we have already obtained earlier without gyroscopic couple. And if we refer back to previous lectures, we had these diagonal terms, all other off diagonal terms were 0 earlier, except these are because of the unbalance. So, here also we have unbalanced component in the horizontal direction, real part, imaginary part, vertical direction, real part and imaginary part. But gyroscopic couple terms are coming in these G matrices, G1, G2, G3, G4, where this G1, G2, G4 will be having this form. So, G1, G2, G3, G4. So, you can able to see that if we want to check one of them like this P11 comma 6, 11th row 6 column. So, in this row is, this is 4 row, because this is 4 by 4, P is 4 by 4, and then this is another 4. So, this is 8, then this is another, this will be 12 and this will be 16, but this entry is at 11th row. So, that means it should come in this particular row. So, 4, 4, 8, and here third, in this third row will be the entry. Now, the column wise is 6th. So, column wise is, here we have 4 columns, because this is 4 by 4 matrix, and then here 4. So, 6th will be second column in this particular vector. So, you can able to see here it will be there, and this is belonging to that particular new entry. So, you can able to see this G3 which is there, this particular G3 will be belonging to this particular vector. Similarly, other 4 entries are there, we have this, this and this. So, they will be coming in this G1, G2, G3, only single terms will be coming, this in whole 4 by 4 matrix. Most of the all terms are 0 except one terms which are belonging to the gyroscopic coupled terms. Now, you can able to see that the overall the point matrix is of this form. Now, we can able to take up some example to illustrate how this we can able to use it, and we can able to calculate the world frequency. And in this particular case, you can see the G is this one, in which now omega is the spin speed of the shaft, nu is the world frequency, that is the natural frequency of the shaft, and now both world frequency and the natural frequencies are appearing. That means, natural frequency will depend upon now on the spin speed of the shaft, that we already seen in the gyroscopic effect when we discussed that particular topic in detail. So, we have seen the derivation of the gyroscopic effect, how the point matrix get affected with that. Now, we will through one example, very simple example, we will try to see how we can able to obtain the Campbell diagram. That is nothing but the variation of the world frequency with the speed using this transfer matrix method. So, for this I have taken very simple example, cantilever rotor. Basically, this is a massless shaft. The disc is having both mass and diametral mass of moment of inertia, even the polar mass moment of inertia, and we are considering the gyroscopic couple in this case. Now, because we have only two stations 0 and 1, we can able to write the state vector relation like this, where T is the overall transfer matrix, which is multiplication of the field matrix and the field matrix and the point matrix. Field matrix will not change as we have explained in the previous lectures. It will remain same, only in the point matrix, as we have discussed today, will change some of the components. Now, this point matrix is given like this, where G symmetric and G skew matrices will be defining. So, first let us see this particular problem, various dimensions. So, you can able to see shaft length, diameter is given, mass of the disc is given, its radius is given, this is thin disc. So, from there we can able to get the other inertia property. So, we are considering gyroscopic couple and obtaining the Campbell diagram also, so that we can able to calculate two critical speed of the rotor system. So, this matrices P matrix is this, which is exactly same as the without gyroscopic case. This gyroscopic matrix additional terms which are represented as symmetric and skew symmetric is given here. So, you can able to see what will be the form of the point matrix, modified point matrix for this case. We are not considering any external force here. So, field matrix will be of this form, only diagonal terms will be there, there will not be any off diagonal terms, and one of the F will be same as we obtained earlier for the without gyroscopic case. The state vector stacking is in this form. So, horizontal real, horizontal imaginary, vertical real and vertical imaginary components, and one of the state vector is represented like this. So, one is having 4 by 4 into 1 size. So, total will be having 17 into 1 size, because this is 4 into 1 size. There is no unbalance. So, this vector will be 0. Now, the multiplication of these two to get the overall transfer matrix will give this form of the matrix. The state vectors at 0 station and station 1 are given like this. Here we have applied the boundary condition also, because at 0 station we will be having we have fixed end. So, displacement linear and angular will be 0, both the real part and imaginary part of that. Similarly, here we have for even in the vertical direction and horizontal, this is for the horizontal direction, this is in the vertical direction. So, vertical direction real part, vertical direction imaginary part. So, these are the angular linear displacement and angular displacement. So, this is coming because of the fixed end condition, and at node 1 we have free end. So, bending moment and shear force components will be 0 for horizontal real part, horizontal imaginary part, horizontal vertical real part and vertical imaginary part. So, these are the application of the boundary condition onto the state vector. So, now you can able to see in this basically we have this form of the transformation. So, in this particular vector, whatever the terms are 0, we need to take out those equations. So, in this we have third equation, fourth equation, 7th, 8th, 11th, 12th, 15th, 16th, which will be having 0 entry here. So, we will take out those equations only and we will stack them in a and we will be stacking them. So, basically we will be getting total 8 into 8 matrix, 8 into 8 matrix. So, this will be the homogeneous equation, because this big equations we cannot able to write it. So, numerically we need to solve this, but basically we will be getting the homogeneous equation as 8 by 8 matrix, and that can be solved for various values of omega. So, you can able to see that we are solving that particular 8 by 8 matrix determinant for one of the speed. So, here we have taken 0 speed, and when we are solving it, we are getting 2 terms. You can able to see basically they are approaching to 0 because of the numerical difficulty. They are not approaching here, but these functions are becoming 0. So, that means this is one of the natural frequency of the system, this is one of the natural frequency of the system, this is the determinant of the homogeneous equation, basically the frequency equation. This is for the frequency equation. So, these are the two roots, because speed is 0. So, there is no gyroscopic couple. So, we are getting only 2 critical speeds or 2 natural frequency. But if we take some other speed and solve the same determinant, then we will get, you can able to see that there is splitting of the frequencies taking place here also. So, now we are getting 4 roots. So, basically they are all intersecting to this 0 line to some value. So, we will be getting 4 natural frequency. Similarly, if we increase the speed to 1000, we will see that separation of these speeds will be more and more. The separation will be more as compared to the previous one. Even if you increase to 1500, you can able to see separation is more. So, basically if we vary the speed and pick up all these frequencies and plot them with respect to speed, we will get the Campbell diagram. So, basically you can able to see this is the spin speed, and these are the 4 natural frequency which we are getting. So, you can able to see that at one particular speed, let us say 1500 here, we had 4 intercepts, 1, 2, 3, 4. So, those 4 values are belonging to 2 here and 2 here. So, similarly we are varying the speed in this range, and we are obtaining various points along these lines, and at 0 speed we have seen that they are meeting at the same point. So, there is no splitting at 0 speed. So, you can able to check with the 0 speed what was the value. So, it was around below 200. So, around, and this is above 800. So, approximately I am checking. So, this was below 200 the first root, and this was above 800 second root, and as we increase the speed, the splitting is more and more. Now, if we draw a 45-degree line here, which will belong to the world frequency equal to spin speed, we will see that they will intersect these lines at 4 places, and they are basically 4 critical speed of the rotor system. So, 1, 2, 3, 4 intercepts will be there, and all these values are the critical speed of the rotor system. So, this is the Campbell diagram, which is nothing but the variation of the world frequency with spin speed, which is occurring because of gyroscopic couple. And if we draw this particular line, which is the synchronous world line, in which the world frequency is equal to speed, we will get the critical speeds of the rotor system. Today we have seen the transfer matrix method two main aspects. One was the how to handle the support, intermediate support in the rotor system, and we developed the transfer matrix for that support itself, and we have seen how we can able to get the frequency equation for such cases. Then we extended the method for more complex phenomena, that is gyroscopic couple phenomena, and we have seen that only 4 terms in the point matrix, the modified point matrix, are getting affected, and only difficulty is with that the world frequency becomes the speed dependent, and because of that the solution of the world frequency for each of the speed we need to obtain, and basically that we can able to represent using Campbell diagram, and Campbell diagram then we can able to use it to obtain the critical speed. Now in the subsequent lecture we will be considering the finite element method, which is more powerful and more popular nowadays. In that particular case we will see that how the boundary conditions like support reaction they can be easily handled.